In this video, we are going to see about detection of contact lens from iris images during recognition. Human iris is still now considered as the best biometric trait for authentication due to its accuracy and performance. In order to overcome the easily guessed passwords and tokens used, have been encouraged to create a strong passwords by using biometric techniques like fingerprint, palm print, iris, and other physical and behavioral traits. It contains the rich textual information which serves as a key information or data for identification purpose. This contact lens in iris recognition can be spoofed easily using a plastic eyeballs, printed iris, and contact lens. Attack on the soft contact lens is more challenging as it contains transparent texture than can blur the iris texture. Here comes the main phases of iris recognition system. First is iris image capturing and the next is iris segmentation, which is done using Huffman transformation. And the third one is normalization, which can be done using pseudo-polar normalization. And the fourth phase is future extraction, which is nothing but GABA filtering. And the fifth phase is recognition, which can be done using a Hamming distance. Iris recognition is an automated method of biometric identification that uses mathematical recognition techniques in both video and the images of the iris of an individual. Iris recognition is a biometric that depends on the uniqueness of the iris. The iris is a unique organ that is composed of pigment vessels and ligands, forming unique linear mask, slight ridges, grooves, furrows, vascularite, and other similar features. Comparing more features of the iris increases the likelihood of uniqueness. Since more features are being measured, it is less probably for two iris to matches. Here comes a pre-processing stage in which from the image captured before the pre-processing is done. First step is to remove the noise from the image acquired. The noise may arise due to eyelids and eyelashes or marked regions. The noise factor affects the accuracy and speed of iris recognition system. So, due to the noise performance of the iris segmentation or recognition, this system gets down so that the performance of the iris depends on the processing. And how it is detected. It is detected using a canny edge detection or a Gaussian filter or meanwhile other filters like median or mean filters. How the canny edge detection is performed, as it will be result in the perfect edges in perfect and a strong and healthy manner. Canny edge detection involves 5 steps: smoothing, finding gradient, non-maximum suppression, thresholding, and edge detection. As said earlier, canny edge detection helps in detecting the edges of the images, so that here first comes the smoothing, which results in the noise reduction, which can be used because of a Gaussian filter. And here generally smoothing is done to reduce the noise within an image or to produce a less pixel image. The high pass filter possesses the edge reduction. Sharpening a high pass filter can be used to make an image appear sharper. When image consists noise, then the system level performance will get reduced. And in order to find the gradient of the image, edge magnitude and the directions are computed. It is to find edges where the grayscale intensity is high. Image gradient can be used to extract information from the image. Each pixel of the gradient image measures the change in intensity of the same point in the original image. To get the full range of direction, gradient images in the x and y directions are computed. After gradient images have been computed, pixels with large gradient values become possible edges. The third step of the non-maximum canny edge detection is non-maximum suppression. The main motive of a non-maximum suppression is to convert the blurred edges in the images of the gradient to the sharp edges. Remove noisy pixels by considering the neighborhood pixels. Non-maximum suppression works by finding the pixel with a maximum value in edge after selecting all the local minimas in the images and suppressing all the local maximas, and keeps which has a high gradient magnitude. And the fourth phase is thresholding. It is a non-linear operation that converts a grayscale image into a binary image. Here, the useful pixels are identified using two thresholds. Now, fifth step is hysteresis, which is nothing but the edge tracking using hysteresis. Strong edge detected were considered if any weak edge is connected with strong edges, and it is also considered. Here we go for a segmentation phase in which we use a half circular transformation and half line detection, which is nothing but in order to detect the circles present in the iris image, sclera, pupil and iris, we go for a half circular transformation. If any other circles are present in an image, it is also detected using a half circular transformation. And why we are going for a half line transformation is that in order to detect the eyelids and the eyelashes present in the images, which can be occurred as an error, so that we go for a circular line transformation. First, in circular transformation is a basic feature extraction technique used in a digital image processing for detecting circles in imperfect images. A half circle transform is an image transform that allows for a circular objects and lines to be extracted from an image even if the circle is incomplete. The transform is also selective for circles and which will generally ignore elongated and stretched ellipse. This transform effectively search for object with a high radial of degree symmetric. As a result of this segmentation, we obtain a result as images that contains the detected circles in it. The third phase of the iris recognition is normalization. The segmented image is normalized using a pseudo-polar normalization after the iris region is localized, which is using a half transformation. And the next step we process to normalize the region is to comparison between the iris pattern. There are some algorithms to normalize where we perform a pseudo-polar representation. This pseudo-polar representation unwraps the iris pattern into a rectangular shape of a constant size depends on the detected boundaries. After the detection of the circle, it should be converted into a rectangular template pixel values. Pseudo-polar normalization is proposed by a Dachmann, remapping each pixels in the iris region to a pseudo-polar coordinate into a rectangular array, which is guided by two parameters, which one is r and the other one is theta. R represents the radial coordinate and the angular theta is nothing but the angular coordinate. Array with a pixel, consider array with a pixel of 5 cross 9 and remap the iris coordinate into the rectangular region. Pupil and the iris is divided into many concentric circles. For the radial coordinate, how it contains information of how many concentric circles, and for the angular coordinate, it consists of information of possible values lines in a circles, or it can also be predict a particular values. Remap each pixels within iris region from Cartesian coordinate to pseudo-polar coordinates. Reconstruction of iris region from Cartesian coordinates is x and y, and to a normalized polar coordinates is considered as r and theta, which is nothing but the radial coordinate and an angular coordinate. Consider xp and yp are the coordinates of the sample point of a pupil, and xl and yl are the coordinates of a sample point of a limbus along the direction theta. XPO and YPO consider it as an pupil center coordinates, and XLO and YLO is considered as a iris center coordinates. As a result of this normalization, an image is converted into a rectangular coordinates. Comes the fourth phase of the iris recognition, which is a feature extraction. In pattern recognition and in image processing, feature extraction is a special form of dimensional reductionality. The main goal of the feature extraction is to obtain a most relevant information from the original data and represent the information in a lower dimensionality space. In order to extract information, we propose 1D GABA filtering, the GABA channel named after Dennis Gabring, preparing application for edge detection, texture animation, feature extraction, and so on. GABA filters are applied to the images practically a similar route as a conventional filters. At a point when a GABA filter is applied to an image, it gives the most noteworthy reaction at the edges and at focuses where texture changes. A filter reacts to a specific feature implies that the feature has a distinctive intensive at the spatial area of the feature. Now the 1D GABA filtering has also a log which consists of two parameters, central frequency and the bandwidth of the filter. After convol of an image with varying bandwidth will get complex number because the filter bank is complex as a default, and it results in a complex number. It extracts the magnitude and the phase separately. During the generation of the iris code, only the phase information is considered, where here phase is quarantines into your 4 levels and encoded on the bits. In order to compute the magnitude and the phase, we go for magnitude is nothing but root of a square and b plus b square. And for a phase, it is considered as a tan inverse of b divided by a, where here real numbers are converted into a binary numbers, which can be used by a technique called quantization. The phase is the most important method used here. It is robust against various eliminations. It is encoded into binary code as iris is composed of binary bits. Encoding is done through the process of quantization. As for coding, make use of a grayscale levels, and here the imaginary part is the most considered one, and it results in a complex number. In order to recognize the image, we go for a Hamming distance. The Hamming distance gives a proportion of what number of bits are the same between and good for no patterns. Utilizing the Hamming distance of 2-bit patterns, a choice can be made regarding whether a 2-bit pattern were created from various irises or from a similar one. Hamming distance is used in the comparison of two binary strings. It computes the number of a bit position in which two strings are different. Consider or assume you have two characters x and y in which the bits are filled in a binary format. So, when the size is same, start comparing each and every bit which its corresponding bit position. If the bit appears same in corresponding x and y, then check for the next bit, where if unmatching scenario occurs, then consider each unmatching bit and calculate the Hamming distance. In case during the enrollment phase, if the image is of a proper captured coordinate, and during the recognition phase when an image captured is not in the correct coordinate, it may slightly difference. So when compared to the enrollment image, it shifts a bit left or right of us, and it is also considered. It can be 1-bit shift or a 2-bit shift as it depends, and calculate the Hamming distance. Thank you.